So just give you a short introduction about the talk. In this talk, I'm mainly going to discuss about how some theorems in the mathematics are so profound and so mind-boggling that it can break literally the whole base on which the present cryptography works. And this talk contains about many concepts and many theorems. The sole purpose of giving this talk is to create a curiosity among you guys to search about it, as in the 12 minutes it's very hard to cover all the topics. The main thing I will discuss in the talks, we start with the Riemann Zeta function, then we will move to the prime counting function, then we will talk about the RSA encryption algorithms, and at the last, how the main question, how to earn money through mathematics. Yeah. So this is a Riemann zeta function. It's nothing just a summation of 1 by 1 square plus 1 by 2 raised to power f plus 1 by 3 power s till infinity. Seeing this function doesn't give you much of an idea of what it is, so we will use something called a complex analysis transformation to understand what to visualize this function. And just to know that the s can take a complex value, so it is actually taking a plane as an input and giving a plane as an output. So just plotting doesn't make sense as we can't see 4D. So we will use this method, and what this method do is simply explain with the help of this video. For any input, we every complex function can give output. We will simply take a simple h square as a function. So we know that 2 will be mapped to 4, minus 1 will be mapped to 1, and iota by its definition will be mapped to minus 1. Now just take one of these points and just pay attention how it gets transformed. And it will just hold, rotate, the plane will get rotated to give us a output. Okay, very confusing. Let's go it again. So this is what we call complex analysis of a function. It's simply mapping its input to the output on the same plane. Now, if we do the same with our Riemann zeta function, this is what is the output. Don't you see it's the one of the most beautiful thing with the mathematics, can it can create the pattern that no one could even imagine. But there is a weird thing happening here. That is, it feels like the function is trying to get out in the negative plane, but there is like a sword imaginary line which has cut into the between. Like there's a beautiful pattern happening, but it got suddenly cut in the between. Now there is a mathematical formation called analytical continuation. What this do is it's simply when the function is undefined in certain areas, we use simple graphing tools and derivatives, and as we know, mainly calculus, to extend it into that area. To be precise, this function is not defined in this area where we use analytical continuation, so there will be a new definition for that function. So if we continue our Riemann zeta function, it just gives us a more beautiful pattern. Now, people might be confused why I'm just talking about Riemann zeta function for so long. You will see it in the why. Now, if we just take a one single line about this, you can see the yellow line coming. This is actually the line which responds to the x equal to half. This is a very beautiful line, and it will take you to one of the most mind-boggling results known as a Ramanujan summation. But more about it a bit later. Let's see some interesting results that it can give when we do analytical continuation. We see that the all negative even numbers are mapped to zero. And this are known as trivial zeros by mathematical term. Trivials means which is obvious, but if we can see this is not much obvious, that is give out the result as 1 square plus 2 square plus 3 square all to infinity is equal to 0. Not only this, it's even give out that the sum of number raised to an even power till infinity will sum to 0. Mind boggling? Wait for a while. Now, minus 1 gets mapped to minus 1 by 12. And all the math geeks knows that this is what Ramanujan said. 1 plus 2 plus 3, the sum of infinite integers, positive integers, sum up to negative 1 by 12. And all these things, which once we thought as just a mind-boggling or just a random results, suddenly came up from a single function. Now that function that we created in the left half, which is which is not obviously the zeta function, it is the extension function. Mathematicians do have derived it. We know most about it, but there is a mystery that is still unsolved, and it is not a small mystery; it's a mystery worth 1 million rupees, and that what is called the Riemann hypothesis. Now, what Riemann hypothesis is that we already figure out that the all negative even numbers are zeros. They are called trivial zeros. Now there are non-trivial zeros. First, we found out that all these non-trivial zeros are present in this critical strip, which is present between 0 to 1 of a real number. Riemann hypothesized that no, it's not only in this critical strip, all the non-trivial zero exist in the critical line defined by half plus a iota. Means all the non-trivial zero will have the real part as half, and this is a formal definition of it. Now, for me, math is more about graphs and drawings. So I just try to plot this non-real zero, the transformation of this line to its output. And this is a beautiful graph that we get. What is happening is like there is a point moving in the on the line half plus a iota, where a is a parameter, and what the output it give when we put it into the Riemann zeta function is plotting that output. You can clearly see this cuts the 0 0, means the zero number many times, means there are many zero that exist on this line. And I have given the link, so if someone is interested in the Python code of this, it is available. Okay, we talked about the Riemann zeta function. Yeah, it's good. It's weird. Some people will give you 1 million rupees just to prove that it has some roots, non-trivial roots, and its real part is half. Oh, for now, let's keep it on the sides and talk about a different function called prime counting function. It's a very simple function. I will not talk about definition. I will just show you what it is. It is a function where you just raise it up by one when you encounter a prime. Let's say 0 is not a prime, 1 is not a prime, 2 is a prime, so 1 up. 3 is a prime, 1 up. 4 is not a prime, 5 is a prime, 1 up. 6 not a prime, 7 prime, 1 up. Simple function. Let's see how this function behave when it go up to 100. It is exact. Up to 1000, a bit of clean, but yeah, it still have curves. When we go up to 10,000, this found similar, if you know, it's similar to 1 by log. Uh, those who are interested in graphing have just seen and tell this is, it seems similar to the function of 1 by log, but it is not exact. There is a division between both. Now, if we just change this function a bit, instead of going up by just p, we go up by log p. And this is what we got as a function for first 100 terms. Now, this is just the same log p, and I have used a video. Now, the interesting thing about is when Riemann was solving the Riemann zeta function, he came up with a wave. Uh, what was the equation of the wave? For now, we just trust in me that there was a wave. And he realized that if we plot this wave, it's just cut through this uh, prime function. And if we add the zeros, the non-trivial zeros as a harmonics, it will start to curve and take the shape of the function. You can see as we had the harmonics, it will just map to the real prime counting function. And if we add infinite number of zeros, it will actually predict the whole prime counting function. So it simply says that if we can found those zeros of the Riemann zeta function, the non-trivial zero, which has the real part as half, we can actually predict where the prime number exists. And one another way to see the relationship between the Riemann zeta function and the prime is the Euler production, which simply says that the Riemann zeta function is nothing that's the product of 1 by 1 minus p is just all the primes minus raised to power of minus s. So I think till yet I able to pretty much convince you that the solution of a Riemann zeta function will give a lot of information about prime numbers. Now still I didn't answer the question how to become means I gave you 1 million rupees just for solving that question, that that exists number, but we are greedy person. We want to earn more. So let's earn more. Now we will discuss about something called RSA. It is an encryption algorithm, one of the most famous encryption algorithms used. Cut to the chase, let's directly use an example. This is a pre-solved example I just use. That means PU stands for the public key, and there is the output key. Let's say we have a 88 as an input. So 88 raised to power 7 mod 187. Those who know, the 187 is a product of the two primes 7 and 11. It calls ciphered as a text 11, then we decrypt it at text 11. Long thing. Let's try for the example. In the chat, I just want you guys to just tell me a word, your favorite word, and we will just encrypt it and then we will again decrypt it. It will be fun. Any words, random words, those you like? No, not that long word. It will take very long time to just decrypt a single character. I mean, uh, these methods are very long. Blue potato methods. I want a single character. Okay, there are many popping up. Let's take randomly B. All okay with B?
Yes, you can take B. Yeah.
Okay, so let's we have B. Uh, RSA work with numbers. So let's convert B into a number. I think we can map B to 2. Then now you guys just raise B to the our first encryption key, that is 5. Just let's keep the chat active and tell me what's to the power 5 is. 32. Yeah. Now mod it with 14. What is 32 mod 14? Oh, yeah. So our decrypted character means the secret way to send that you are telling me letter B. Instead of letter B, you will send me 4. But now as we are talking in terms of words, the 4 will be mapped to D. So you will send me D. Now how I will know that D by D you mean B means a D is a decryption of B. That's also is very simple. It's given by the decryption keys. What we'll do, like you give me D mapped to 4. I will raise 4 to the first key, that is 11. Now, can you guys just tell me what is 4 raised to 11? Those using laptops or any strong,
कहाँ पे है दारू का दुकान?
sorry,
नहीं,
are you? Okay, it's very long. I accept. It's very long. Can you just rough estimate what in what range 4 raised to 11 might result into? Yeah, some number. Yeah, as Shiva Kumar said, it is a long number. Now mod it with 14. The number you get is 4 is to 11 mod 14. You will end up with 2 again. Means we just saw this is like a very small and very vague example of how RSA works. Now let's see how this is actually connected to prime numbers. Um, we learned for making these keys, that's 5, 14, 11, 14. You see that there is a 14. The 14 is called a public key. It's out in the public. Everyone knows what that public key is. 5 is a private key of the senders. 11 is a private key of a receiver. Now, these keys are related. They're not just a random number. How they're related is just given by this. We will take a two prime number P and Q. For our example, it was 2 and 7, the multiplied to 14. So that will be a public key for everyone. Then we will also define a this notion function. What this notion function actually gives is the number of, it's actually count the number of coprime that exists less than itself. For our number that is 14, if we count this, we have 2 and 7, it will product into 6. So there are actually 6 coprimes. I know for some people it will like lot of mathematics in just a short time. So okay, let me cut this. Um, just to conclude, what I want to say is that the RSA is highly dependent on primes. If you know the two primes P and Q, of which this 14 is multiple of, as of now, you can see the 14 is a multiple of 2 and 7, two primes. With just this knowledge that it is 2 and 7, you can actually figure out 5 and 11 both. So what is secret in it? The secret is that when the companies use RSA algorithms, they use very, very large primes. So primes that range up to 100 or sometimes even thousands of digits. Now, as we don't know what is the distribution of prime, it becomes almost impossible to factor it. They will take two very large prime, multiply it, and make it their public key. Everyone knows that public key, but it is almost computationally impossible to just brute force and find its factors. So RSA till now works fine. But as we showed a few more moments ago, that using the Riemann Zeta function, we can actually predict where prime number exists. We can say that there will exist a prime here and prime here. We know the distribution over which prime is scaled. And with the help of the distribution, we can approximate, okay, this large number must be multiple of something of this range and this range. And then we can use this Riemann zeta function to find out what are the primes which are in this range. So actually, we just by solving the Riemann zeta function, we broke whole RSA algorithm, which presently actually secure money or assets worth trillions and trillions of dollars. So yeah, this is a simple way to become a millionaire. Anyone interested can go for it. Any questions? These are the reference video. The video that I've used in my PPT are actually taken from this YouTube channel. So shout out to them and open for questions.
So I guess you can see in the chat box, someone asked, does this mean RSA is not secure?
RSA is secured until you can't prove the Riemann zeta function. The point the Riemann zeta function got proved, RSA will just break out into pieces. And just to know how, I mean, about Riemann zeta function, Clay Institute announced this that we will give you $1 million to solve this, to prove this Riemann hypothesis. And they declared it in year 2003. Until yet, no one has solved it. And this Riemann hypothesis is in the picture from last 1.5 decade. Means in last 150 years, people were unable to solve this. So as of now, we can say that RSA is pretty secure. But
Okay.
if you
Okay. So any other questions? Okay. So I have one question. So can you go back to the previous slides, like uh, where you have computed some sum?
okay, yeah, that mm, mind-boggling. Some wait, this one.
Okay. So is it correct?
Uh, okay, so this are, is it correct or not? This whole argument is based on what we perceive as mathematics.
Sorry.
Uh, uh, the argument, argument that it is correct or not, solely depend on what we perceive as mathematics. Now, for a normal person, this might seem incorrect, but as we saw, there are extension of function which give this as a result.
Okay, so so I just quickly I just want to finish this. Okay, this is actually incorrect. Okay, so in some sense, Ramanujan made a blunder actually. So he mixed two things. Okay, so the left, so Ramanujan actually predicted this right hand side. Okay, but the left hand side is incorrect. Okay, so if you analytically extend the Riemann zeta function, in the left hand side you will get something different. You will not get this sum. Okay, so I just want to quickly this. Okay, so. These two statements they're incorrect. Okay, so that is what I wanted to tell. Okay, so you can write it, but so the problem is Ramanujan made a mistake. Okay, so his prediction was correct. Okay, this the Riemann zeta function gives minus 1 by 12 at 1. Okay, but if you put 1 at the Riemann zeta function, you will not get that you are getting on the left hand side. Okay, so okay, okay, means yeah. Okay, so that, yeah. Thank you, Tirth. Uh, so I guess now we have a lunch break. So we'll resume at 2 o'clock. Okay. Okay. Thank you. Yeah. Thanks.